Okay, so hey everyone, good noon. Thank you for coming to my presentation. Today I'm going to present to you research that I've done on an iOS kernel module, an iOS driver called Apple AVE driver. So the main agenda for today. First, I'll review some of the core attack vectors on iOS and some of them actually also related to macOS. Second, I will present the vulnerabilities that I found, some of them. Then we'll get to the exploitation part, of how to actually take those vulnerabilities and take them into a fully working exploit. And then a few words about jailbreak and a small surprise. And finally, Q&A and disclosure timeline. So a little bit about myself. My name is Adam Donenfeld. I'm a security researcher, work mainly on iOS and Android. I do vulnerability assessment and exploitation, so more on the offensive part. And currently, I work as a senior security researcher for Imperium. Additionally, I would like to thank Tsuk Avram and Yaniv Karta for helping me with the presentation and supporting me during the times of frustration. So let's start. We'll start, like I said, with the review of the attack surfaces. So in iOS and also macOS, there are a lot of attack surface. We can categorize them into different sections, let's call it this way. Mainly syscalls, system calls. Now on iOS, on GNU, we have Mach syscalls and FreeBSD syscalls. We also have MIG, which is an auto-generated messages interface. So you can just put, it works like an IDL. You write an IDL templates, and then some code is auto-generated. And finally, we have IOKit. And by the way, IOKit is profoundly based on MIG. So to actually issue IOKit calls, eventually everything goes through MIG. But IOKit is a huge platform, and even though everything is going over MIG, it deserves its own bullet here as an independent category. So 60 seconds about IOKit. So IOKit is Apple's collection of resources, tools, frameworks, and everything for creating drivers for GNU. Unlike Linux driver, for example, those drivers are actually written in C++. This is done because you have some macros which gives you some basic reflection capabilities, which is super cool in my opinion for drivers. And additionally, you have some layers, some isolation between an actual driver and the communication channel of the user mode and the driver. Again, if we compare it to normal Linux drivers or Windows drivers. Additionally, Apple gave a huge amount of built-in types. You have pre-built dictionaries, arrays, integer strings, and you do that. You have those types from Apple. And finally, I think this is the best gift Apple could give to offensive researchers, because it's an amazing platform for exploitation of this new kernel. Now, I want to review some of the projects that dependent on IOKit. So as you can see, that's a list of recent jailbreaks that were based on IOKit vulnerabilities. It's not the full list. The only reason I actually didn't write more of them is because I didn't have room on the slide. But there are more jailbreaks and projects, and obviously, probably, more attacks that are not jailbreaks, which depend on IOKit. Now, the question that probably most of us ask is, why hackers love IOKit so much? What makes IOKit such a good platform for attacking? So first of all, there are a lot of drivers, which definitely increase the attack surface. Now, there's no, I mean, we don't really know that for 100%, but I believe the people who work on IOKit don't really work on GNU, and that's why there are some miscommunications between those two groups, which leads to bugs. IOKit is, like I said, IOKit is written in C++, and which means those are actually objects. So for example, you have vtables. Now, if you can override something and you can override a vtable, you can override function pointers and you can hijack the kernel very easily, which is, by the way, something that you can also do to bypass the new KPP and MCC mitigations, because those are not protected. Finally, because most of the IOKit drivers are not open source, less people audit that code. I think it's a mistake, and I think IOKit's in terms of security is undermined. I mean, GNU is a little bit more protected, in my opinion. Again, just my personal experience. So, how do we actually use IOKit? How do we actually communicate with drivers? So, the first thing we do, I just wrote a basic snippet here to get a handle to a driver. So, this function gives out a connection to a driver, which is, by the way, just a port. And it gets a name of a driver that it has to look for. So, the first thing we do, we get the IO master port. By the way, this is, like I said, IOKit is essentially based on MIG. So this is a MIG call, which gives us back the master port. The master port is used to get a list of drivers. So here we say, yeah, give me all the drivers which are based on IO service, which is all the drivers, as we will see soon. We get an iterator back, and then we can iterate all the drivers. We get the name of the driver. We check the name that we are currently running on, and if that's the name we want, we just call IO service open, another API that uses MIG, to get a connection to the driver. So as you can see, master port gives us an iterator, which gives us a service, like we can iterate a service, and a service gives us eventually the port. So how do we actually write drivers for iOS or GNU? It's actually not really documented, and I personally understood how to do that just from reverse engineering drivers, which is kind of fortunate. So those drivers have an external methods. If you're familiar with Linux, it kind of reminds IOCTL. Drivers overwrite the external method function, which is called every time the user wants to communicate with the driver. The users issue those comments using an API called IOConnect call method. We'll see an example soon. So like I said, the drivers must overwrite the external method, and because everything is based on MIG, everything is based on messages, because MIG is just messages. So again, IOConnect call method ultimately calls mach message. We'll see soon the flow. So that's the signature of the external method functions that drivers have to overwrite. What the user gives is an index. That's the selector. So that's just an index to a command, let's call it this way. It also gets arguments, which is a struct that contains the input buffers and the output buffers from and to the user. Dispatch is the pointer that's dispatch is the function descriptor, let's call it this way, the function descriptor that will eventually be called. Target is the actual driver, and reference is something that I actually never saw. I never seen any driver using it actually. So that's an example of the override of that function. So like I said before, the selector is something the user supplies. So obviously, because it is completely controlled by the user, you have to check that this is the actual method count, that it doesn't go beyond that count. Then the driver takes the appropriate function block. This is the external method dispatch. It takes the function block, like the function descriptor. It takes it, it puts it into the dispatch. Target is the driver itself. because like I said in the beginning, there is an isolation between the connection of the communication of the user and the driver. So that's the driver, and this is the communication. And like I said, ref is never used. And then the implementation of external method is being called the IO user client implementation. And this is just checks that the user buffers are in the appropriate size with the function block. And that's actually that's ultimately calls the function. It's not necessary to call that, but that's the appropriate way to do it. But you can do it yourself also without calling this one. So we saw how the drivers implement it. That's everything you have to know to actually implement the most basic user-driver communication. Now let's see what the user does. So that's the function I showed before. That's the driver we're trying to communicate with. So Apple AV icon, it is just the communication with the driver. That's the handle to the driver. Now we call function with the index 0. So our selector is 0 here. We create a struct, an input buffer in the size of 8 bytes, an output struct 4 bytes, and we actually, because the output, the size might be different, we actually have to supply a size parameter, which the kernel can override. So like I said, index 0, and we can see that here because selector is now 0, it takes the first descriptor from here. So in our case, S open. Like here, you see that the input is 8 bytes, the output is 4 bytes. So here, 8 bytes, 4 bytes. And that's it. That's the whole thing between user and driver, like the basic communication. So again, the whole flow, user calls IOConnect call method. We see it here, IOConnect call method, which calls the MIG function, IOConnect method, which it calls mach message. It wraps into the kernel. The kernel gets into X IOConnect method, which calls IS IOConnect method, which eventually calls the driver's external method implementation. So far, that's everything about the code. Now let's see how it actually looks in the binary. So this is an example from the driver, Apple AV driver. Like I showed you before, that's exactly like in the code. You have a pointer to a function. You have the struct input size. You have the struct output size. By the way, these two zeros are if you want to just pass an array of integers, but I mean, you can just pass an array of integers, but you can also pass a struct, so it's up to the driver to decide. So that's it. Now we know more or less how drivers work and how users communicate with them. So now let's see the vulnerabilities. So here's a list of the vulnerabilities I found. One of them is in IO surface. I'm not going to get into that vulnerability, but the details are available online, and if you want more explanation, feel free to ask me about it. What I am going to talk about is some of the vulnerabilities I found here. I didn't have to use all of them to actually write a full exploit, but I'm going to show a few of them that I didn't use, just to learn. Now, in order to understand some of them, we have to talk a little bit about IO surface. So 60 seconds about IO surface. IO surface is a kernel object which is used to share hardware accelerated graphics data. So frame buffers, for example. You can share them across multiple processes. The advantages of using an IO surface object and not actually send the frame buffer data is that IO surface maps the data. So instead of sending now gigabytes of information, you can just send an IO surface object. The process asks the kernel to map the data that the IO surface object handles, and then the kernel just maps the data. So it's just the mapping of the same physical memory, which saves a lot of time, and it's a very convenient way of passing a lot of information. IO surfaces are shared by an ID. You can create a global IO surface, so anyone can map that information based on an IO surface ID. You can create private ones. It doesn't really matter for our specific case, but still nice to know. So to summarize it, IOSurface is just an object that allows you to transfer data. So now, what is Apple AV driver? So Apple AV driver is responsible for hardware accelerated encoding, video encoding in iOS. It's not available on OS 6, unfortunately. There is absolutely no information or documentation about it on the internet. And unfortunately, like most of the IOKit drivers, there are no source codes, which means that I had to reverse engineer it. So here's the table of the external methods of Apple AV driver. I just removed the properties of every function so it gets into one slide. But one of the things that really attracts my attention in that table is that one of the functions required a very large amount of input, which I could somehow understand because, yeah, videos have a lot of properties, so maybe I don't really know what's going on. I mean, for a first glance, it looks suspicious, but, you know, it's not like I can do something about it. But it also gave a lot of information out, which is also something that usually you wouldn't expect from a driver. So I started reverse engineering that function, also set session settings. That's the name I gave to the function based on logs from based on the prints in that function. So I spoke before about this function descriptor. So you have a function pointer, input count, and output count. So a buffer, sorry. So the input buffer is in offset 30, and the output buffer is in offset 58. So x1 is the input buffer, x2 is the output buffer. Now let's see what the function does. So first of all, we put here so the input buffer gets into x19, and the driver itself gets into the connection, sorry, gets into the x20. So it fetches something from our input, some keyword. Then if we actually put something in that offset, which we completely control because that's the input buffer, if it's not null, then we jump here. But if it's null, we see that it gets something. It gets some integer from our input, which after reverse engineering that function, I know that this is an IOSurface ID. Then it just gets the IOSurface ID. It puts it back into offset 178 into the input buffer, which is not readable from the user anymore, by the way. And then it continues further. Now, what we see here is that we can supply something, and if we don't supply it, the kernel puts there a valid kernel pointer and continues on, which means we can get the kernel thinking that we have an IOSurface object control, and we can supply any address we want, and the kernel will believe that this is indeed an IOSurface object. So to summarize the primitive we have here, we can supply any kernel address we want, and the kernel believes it's an IOSurface object. Now it's important to mention, we can also supply a user mode address, but because I wanted to bypass the SMAP or PAN mitigation that are in the new versions, I'm sticking to kernel pointers here because the kernel will not accept user addresses if that mitigation is enabled. So one thing that surprised me with that behavior is that why is the kernel expecting the user to actually give in kernel addresses? So I said it must probably someone supply those kernel addresses to the user. So I looked for that, and in selector number 7, I saw that just like before, we can supply a surface ID. It puts that into the input buffer. But then for some reason, it takes it from the input buffer into x9, and it puts it back into output buffer. So what we get here is an info leak, so we can supply any IOSurface ID, which is completely something that is it's not really user mode, but it's something that you could share to talk about a specific IOSurface. And we can get its kernel address, which is completely something that the user is not supposed to have. So let's summarize what we have so far to actually craft the exploit. We can fake an IO surface object, which is an IOKit object, so it has vtables. So we can fake a vtable, which means we can hijack the kernel code execution. We also have the address of that IO surface, which means we have the we can bypass map because we can still stick to kernel addresses. The only thing we don't have is some way to bypass KASLR. So that's the last thing we have, and then more or less we have all the bypasses for every mitigation in order to hijack the kernel code execution. So at that point I said, okay, this driver is very interesting. Let's dig further to what it does. And I saw that eventually all of those functions lead to the same code, to the same function. So all of those selectors were just wrappers to the main logic. By the way, command gate, if someone is interested, it's a synchronization mechanism in iOS and OS X. Not really relevant to this example, but that's also very important to know. So that's how the main logic looks. Really unpleasant if you have to do a quick reverse engineer. Nevertheless, I had to reverse engineer it to understand what's going on. So let's quickly brief it. So the driver is put into X20. The user client, like the communication channel of the user, is put into 22. Something which we are not exactly sure what is put into 21. And 25 is our input buffer. So what I saw somewhere is that it takes, like I said, 25 is our input buffer. It takes from X25 a surface kernel address, which we can control, but we can also put a valid kernel address here. So X1 is an iSurface kernel address. It gets also a lot of other information, not really relevant. I'll summarize it because it's not the important part here. What it does, it gets the iSurface object, and then, like I said before, it maps the iSurfaces are meant to map to shared information, so it maps the information to another address space. So what eventually it does is it puts into X26 the map of the data of the iSurface. So everything X26 points to a kernel address which we fully control its content, and because it's mapping, we can also modify that data during the execution, which unfortunately the kernel didn't consider at all. So nothing is locked in buffer. Everything that is in this buffer can be changed anytime. What I saw eventually that the kernel does is, here's the X23 is the kernel address of that mapping. It takes some command from X23, then there's a switch case. One of the examples that I saw in that switch case is that it takes a kernel address from that mapping. It checks if this kernel address is not null. If it's not null, if it's null, it allocates some data, puts it back into the mapping, which is also an information disclosure because we get to have a kernel address in the size of X28. And because it's a mapping, we can read it. And then it takes that pointer and it initializes it. So not only it's an info leak, but we can also initialize the first X28 bytes of any kernel pointer we want, which is by itself might sometimes be sufficient to create a full exploit. But why bother when we have such better primitives here? So again, our goal is to eventually get the kernel base to bypass KASLR. So eventually it gets to some function which is called map YUV input from SACE-ID. Again, that's the name because I gave it from the K prints. But we don't really have to understand what it means to find the bug there. So it gets the iSurface kernel address into X3, puts it into our mapped data, loads another one, do it again. And what it eventually does is X23 is our mapping. So it takes an integer, a controllable integer from there, and it also takes a pointer from there. And then x2 is gets into here, and x2 is a pointer we completely control. Now, I put the code here into as pseudocode because in assembly it's a little bit more annoying. So, and I want everyone to understand. So, controllable pointer is the mapped pointer we put there from here. So it's something we completely control. It puts there a mapping, then it extracts the address from that pointer. And then what it does, from that extracted address, it dereferences this address in specific offsets into our controllable pointer. Then in some offset, it checks whether this, is it checked the keyword, it checks whether the high 32 bits are 0, and if they're not, the kernel panics. So this is a very interesting primitive here, because we can put any address we want into controllable pointer, and we can read from that address. So we can have a very powerful info leak. Now, the reason, again, that this is not, the reason that here it's any address we want and not IO Surface Buffer Manager is because this is a controllable pointer. So after IO Surface Buffer Manager is being put here, we can still change the content of that pointer because this is a pointer we completely control. So if we point it into something we control, we can just change it right after it's set here the Buffer Manager. So if we summarize the problem we have here, if we want to leak a specific address, at least one of those rules have to happen. Because if you want to leak address 100, we can take 100 minus 38, and then we have to make sure that that delta plus 50 is not 0, and that's the summarize of our primitive. At least if one of those addresses is not null, we can leak any address to the address. And of course, because this is just dereferencing kernel memory, X has to be a valid kernel address. So here we have an info leak. We have heap info leak. We have sort of a semi-absolute kernel read, and we have kernel code hijack. So we have a lot of primitives. Let's see if we can craft an exploit from all of them. So our plan is as follows. First, we create an IO Surface object. We leak its kernel address because we have the vulnerability that gives us the kernel address from a surface ID. And then we somehow have to leak the kernel base to find the KSLR slide calculation. We free the IO Surface object. We spray data in the same size, so our spray data gets into the same kernel address. We have to assume that it gets into the same kernel address, but statistics show that this is unbelievably reliable. And then we give the kernel address to the kernel, and the kernel believes it's a real IO Surface object, because that's the first vulnerability I showed here. This time we can put a different vtable pointer, for example, which will lead to execution of the kernel to somewhere else we want. And ultimately, our goal is to get kernel read write, give ourselves root, and enjoy our lives. So again, let's see how we take advantages of an advantage of the semi-absolute read. So again, our goal is to leak a constant kernel address, so we can calculate the slide between the leaked address and the original address. So, and again, X has to be a valid kernel address. So we do have a valid kernel address. We have the IO Surface object, which is a valid kernel address. So let's start to see if we can somehow leak something constant from the kernel address. Obviously, the first thing that comes to the mind is the vtable, because it's a constant address, always slided from the kernel address. So that's the IO Surface object. Again, these are the offsets we have. We need x18, 1c, and 3c. So 18 is that, 1c is also that, and 3c is the current, it's the memory descriptor. And unfortunately, this is never null. And a memory descriptor is the actual memory that the object that maps the data of the IO surface. So of course this is also never null. So we can't unfortunately leak the vtable of the IO surface, but lucky for us, IO surface is a very big object. So I just kept understanding what the other parameters, the other variables of the object are. So IO surface creates an object. IO surface maintains a list of something called IO fence. We don't really have to understand a lot about it. It's just a synchronization object that IO surface uses. It actually has a list of those. And lucky for us, after that list, there is a lot of controllable information. These are called bulks. I have no idea what they are actually used for, but we can completely control them. So everything we see here is completely controlled by the user. So we want to leak either one of those lists. So lucky for us, if we control everything here, we are able to actually leak one of an IO fence object. So now once we have it, let's see how IO fence looks, and maybe we can leak its vtable. So most of the offsets we need to be 0 are not null. Lucky for us, the last one is 0 if the IO fence is in a surface queue. Now, because we leaked the IO fence from a surface queue, then it must be in a surface queue, which means completed is never 0 in our case. So we can leak the vtable and calculate the KSLR. So back to our plan, we create an object, an IO surface object, leak the address. Now we can leak a vtable of an IO fence, so we can calculate the KSLR slide, free the surface, spray with a fake object with a fake vtable, and then hijack the code execution. Now, what I wanted to do here is to have the best spray, the best reliable spray ever, so that I wanted to make the exploit as reliable and stable as possible. And now, for those of you who are not familiar with iOS spraying, there is a very common spray, kernel heap spray in iOS and OS 6 as well. IO unserialized XML. You just give an XML to the kernel unserializes the XML object, which, by the way, had a very interesting vulnerability. I think it was last year, yeah? And anyway, but there are a few problems with that. First of all, there is, up to this presentation, I didn't see any persistent memory. So usually the kernel would just unserialize the XML, extract the relevant information, and then immediately free that information. And I also didn't want any limitation on the spray data, and I wanted to be able to spray as many times as possible. And so lucky for us, IO surface maintains a list of properties which are written as an XML data. So by the way, selector 9, for those of you who are interested. So what it does, it just unserializes our data. Then it gets the first object as the value, the second object as the key, and then it just puts that into a dictionary which IO surface holds. That's how the set value function looks like. It just checks that the key is not creation properties, and if it's not, it just calls it just takes the all properties dictionary and puts there the object, which is the key and the value is supplied. So, yeah. So this is very good for us because it's persistent in the memory, because these are all the properties that are being kept in the memory. We can spray pretty much any data we want because there is no specific limitation as long as it's valid, as long as our XML is valid. And we can do that as many times as we want. We can put as many values as we want into the IO surface object, and we can create, I don't think there is an actual limitation on the number of IO surfaces, just the kernel memory limitation. But that's not everything about this spray. And this is the first time I saw a good kernel, generic calloc kernel spray in iOS like that. it's not only that you can put and set those properties, you can also read those properties back, because that's the point of those properties. If you can set them, you can also read them back, which means that we can also, everything we sprayed can be read back. So for example, if we spray the kernel and the kernel modifies our sprayed data due to another vulnerability, we can just read back from any key we want our data. So eventually we can also reread our information. So this is extremely powerful. It can save us, for example, an information disclosure. Because again, if for example we spray an object and then the kernel, I don't know, puts it into a list, we can leak that list if it's a linked list. That's just one example. And this is extremely useful for kernel spraying in kernel heap spraying in iOS and OS 6. Now again, my goal is to, the goals are have arbitrary kernel memory read, write, and I also want to be able to call any function. And I want to be able to do that anytime I want without any statistics in mind, so deterministically. So our current primitive is to hijack, put a fake vtable, so we can hijack any kernel address we want, so we can call any kernel address we want, and we control only the first parameter, which is the actual spray of we had. So now it's time to look for a gadget. So there is now it's a very famous gadget called unserializer serialize. Again, we control x0, so we control both these x1 and x3. Then we control also x9, because it also derives from x10. And eventually x3 is again something we control. So this gives us the opportunity to control the first parameter, x0, the second parameter, x1, and we can jump to any function we want. We are not able to control the third parameter, however. So what I did here, I wanted to be able to I had to put interesting stuff into x10 and x18. So x10 is just the kernel sprayed address plus some offset. x18 is what we will see soon be the third parameter for our final ROP. So x3 is just that, syscatal handler size twice. And x20 is just calling unserializer, OS serializer serialize again. What will happen is that we will get to that function again, and we are going to have to use that as the first parameter. The second parameter is going to be x18 from before, because we control x1. So if we call it again, it's going to be x8. So it's the third parameter. This is the third parameter. And the second parameter is going to be LD cache size handler, which is a syscatal. And the function we are going to call is copy in, which gives us a new interesting primitive. We can call any function we want and control the first 3 arguments, which is enough for a single deterministic write on the kernel. Arbitrary address, arbitrary data, and arbitrary size. So what should we overwrite? So I guess most of you know, there is a new mitigation Apple did. It's KPP or AMCC. So unfortunately, we can't override constants and we also cannot override kernel text, so kernel code. So we cannot override, we cannot change vtables because they are constant. But what Apple didn't protect is syscatal. Now, the reason syscatal are not protected is that they are dynamically loaded, and therefore they cannot be static. They cannot be read-only. That's why there are function pointers which Apple did not protect, and we can override it. So again, our goal is to be able to override, to be able to read, write, and ROP deterministically anytime we want. So what I did, and of course bypassing MCC and all the new mitigations, SMAP and everything. So what I did was I overwrote 2 sysctls, one of them to rope to my sprayed data, to my sprayed kernel address, and the second one is to modify my sprayed kernel address. Again, because I want it to be deterministic. So once we establish a successful single write, I want to be able to establish as many read-writes as possible. So the way it looks is that I have 2 sysctls. So the first one of them overrides our sprayed data, which resides in the kernel. So we overcome the SMAP or pan mitigation. The second sysctl takes a small portion from our spray data and ropes and issues a rope to always serialize based on this data. So again, what I want to do to actually issue any call is call sysctl, call one sysctl to modify my data, call the second one to use my kernel resided modified data, and then we can get to any address to drop or rope to any address we want. So the way it looks is, first of all, we have 2 valid sysctls. We call from our first call. We call OS serializer. We control only the first 2 arguments. We call OS serializer again. This time we control 3 arguments. We call from that, we call again using those controlled 3 arguments. We call copyIn, which overrides those 2 sysctls. And now every time I want to call some function, I call one sysctl. The sysctl calls copyIn, which constantly overrides a specific kernel address, which is our sprayed data. So we override some parameters here. The second sysctl will call the serializer gadget, which will call itself again to control 3 arguments, which ultimately will call our modified data. This way, we can achieve kernel read-write and kernel function call deterministically. So we have kernel op. So how are we going to achieve kernel read-write? So because we can call any kernel address, we can also call copy in and copy out, which means we have arbitrary kernel read-write from the user deterministically. And that's it. That's the capabilities we're looking for, and we successfully achieved them. So a few words about Jailbreak. The exploit is available on GitHub. You can download it and just use it in good, friendly behavior, and not in any unintended way. About jailbreaks, so I said before that I don't intend to work on a jailbreak, not because I'm against it. I think jailbreak is a very important part of iOS. It's just that Cydia, in my opinion, is not good enough. We have kernel exploits. We will always probably have them. Cydia has to be refactored and changed to be able to work good with AMCC and KPP. Now, Ziva, I tested Ziva on 10.3.1 with triple fetch, and I got it to be very stable. So at least 10.3.1 is possible to be pwned if you want to experiment with that. 10.2.1 already has a working exploit for some devices. The only reason 10.3.1 wasn't implemented, in my opinion, it's just because of the offsets. Nobody actually took the liberty of modifying the offsets for 10.3.1. Other than that, I don't see why someone wouldn't use it. By the way, someone did write a jailbreak for 10.2.1 using Ziva. I didn't test it myself, though. So, conclusion, Q&A, little surprise, and the disclosure timeline. So, I must say, Apple are not the first vendor I'm working on. but they have been the best one in communication with security researchers. They are very open and friendly. They listened to my opinions, suggestions, and they actually cooperated with some. I asked them to do some changes in the advisory, and they did it. Unlike other vendors, they never ignored me, which is something that sounds like that's the way to be, but other vendors just stopped the communication for some reason. It is currently, in my opinion, the most secure operating system. However, some work still has to be done, but we are getting there. Apple add new very powerful mitigations over the time. Now, in iOS 11, in iPhone X, Apple fixed all the bugs, and that's it. We can wrap our stuff and go home, or not. So I just wanted to give a little bit, a small sneak peek about a new project we are working on. It's a kernel exploit, this time accessible from the Sandbox, a very powerful kernel buffer overflow. Unfortunately, I can't give more information about that because Apple asked me not to, but I promised to put a working full, at least a full crash, because I did not exploit it to be completely working so far, like a full root exploit. But I think it does have potential. What we see here is iPhone 10, 11.1.2. 11.2 was released this week. I didn't have the time to upgrade and test it. I'm not sure if Apple fixed that or not. I think they did, but I'm not sure. If you want, I also have the device here with me, so if someone wants to see it, like the version and everything, and the device crashes, I don't think it's that important, but if you want to see it, then you can come and ask later. So that was it. Thank you very much. If you have questions about everything, as long as it's not ON ETA jailbreak, but jailbreak questions are also welcomed here. That's the time. Thank you very much. I hope you enjoyed the presentation, and I'm here for questions. That's it. So, any questions? Yeah? Someone is coming with a microphone. Just a second.
Hi, thank you. Very well presentation.
Thanks.
Just a quick question that everybody is always asking, never got a question that answer. How much time this type of thing cost and work, and how much effort?
About the Ziva exploit?
Yeah, well, finding this and exploiting that and making it work.
Okay, so the iOS surface hijack vulnerability and the information disclosure, it was like, I don't know, it was already done on the same day. The problem, the thing that took most of the time was, first of all, the information disclosure. Second of all, debugging those crashes is an unpleasant process. You have to read from a crash dump, you have to fetch it, and with Ziva specifically, because it requires a sandbox escape, each iteration you wanted, you needed a sandbox escape, and Ziva was written before there. I could always do it on earlier versions than 10.2, but actually debugging it is not the most pleasant experience. But from the point where I found the first hijack execution, which was the first day of the research of that driver, till the day I said, okay, we're done, it was within a time range of less than 2 weeks, everything. So I think, and it required more time because I depended on another information disclosure vulnerability, but unfortunately it didn't work out well, not interesting problems. So I really had to work I didn't expect this delay. I think it could have been done in less time, but everything was in 1.5 weeks, maybe something like that. So that's it. Any other questions? I just wanted to more about the questions. It's not always the case. It really depends on the vulnerabilities and on the how reliable you want the exploit to be, how many versions you want to support. A good deterministic exploit, in my opinion, again, depends on the primitive you have. Might take, again, it might take sometimes 6 months, it might take 1 month, it might take 3 days. Again, depends on the primitives you have. So that's my 2 cents about it. Any other questions? Okay, so thank you very much. That's it.